Hello, this is Professor Dan Kernler. Welcome to our next video in our Calc 3 sequence. We are looking here at line integrals in section 17.2. This is our second video. And today we're going to talk about work and how we can look at work when we might have a variable force and how that looks in 2 and 3 dimensions. And then we will also look at circulation and at the end of this section. So first, thinking about Calc 1, when you're Calc 2 maybe, where you have a constant force in a linear motion. So imagine that you have an object that's being moved from the point P to the point Q. And so it's being moved some distance from P to Q. And there's some force acting at some angle theta. You know, in general, that work equals force times distance. But in this case, the force is not acting in the direction of movement, so you'd have to find the projection of the force in the direction of the movement. So that would be the projection of the force in the direction of PQ. Find the magnitude of that and multiply that by the distance that it's moved, which would be the magnitude of PQ. And this is just the dot product of F and the dot product with PQ. Okay, so what about in 3 dimensions then? How does this work if we have a force field, oops, that's Z, where you have the force is acting in a certain direction at a specific point, and the force is not always acting in the same direction. You have some path that you're moving on, say C, and the force might not always be in the same direction. It might kind of vary as you go through here. And so the question is, how much work is done moving the object from the point P to the point Q? So we need something a little more sophisticated for this. So let's go to the next page here and talk about how we can find that force using a line integral. Okay, so let me redraw the drawing we had on the previous page, just a rough sketch here. And we have some path, curve C, and we have some field. Actually, let me go, just to make the drawing easier, let me go in the upward direction. Generally, of course, it's not constant, it's not always in the same direction, and there's a bunch of other forces that we're not seeing. The path is kind of surrounded by forces, but it's moving along, the object is moving along this certain path. If we look at a specific point and kind of zoom in on that point, you have the point is at some x sub I, y sub I, z sub I, and the force at that point is in a certain direction. There's our force. If we look at a small interval, there is some small delta s sub I that the object will have moved in that time interval. And then there is a tangent vector that's tangent to the point and in the direction of motion. So that will get us in the direction of motion. And this force here, to be clear, this force, that force is a function of the location. So the force is not constant. So we have our object traveling along this path, and there's at each specific point there's a force. And so what we need to do is we need to find that force projected onto the direction of motion. But that's the tangent vector. So we can find the direction of the component of the force projected onto the tangent vector, and that will give us our force in the direction of motion. So the delta W sub I, the work for that moving at that small thing, will be the magnitude of the force in the direction of motion times the distance it's traveled, which would be the projection of F, we'll call it of F sub I, onto the tangent vector. And then multiply that by delta S sub I. So that's the dot product of the force vector with the tangent vector, and multiply that by delta S sub I. Okay, so that's the work for that small little motion there. So let's take a look at what that would be and kind of broaden this out and try to add all of them up. So the sums of all of those delta W sub i's, the sum of all those works. As I goes from 1 to n, and then we'll take the limit again as the largest interval goes to 0. The magnitude of that largest one goes to 0. That's the limit of the norm going to 0, this concept we've seen repeatedly. This would be the limit as that norm goes to 0 of the sum, I goes from 1 to n, of all of these force vectors, and to be clear, they are at particular x sub I, y sub I, z sub I, the dot product with the tangent vectors at the x sub I, y sub I, z sub I, times the delta s sub I. And if we add all of those up, we get an integral, and it's an integral over the curve. So it is a line integral over the curve of the dot product of the force vector field, the force with the tangent vector ds. Okay, take a deep breath. We need to know how to calculate this, how to actually evaluate this, because we don't know, like, well, what is f, what is t? So let's talk about how we can actually evaluate the line integral of a vector field. Well, given some path r of t, we know the tangent vector is the magnitude of, or is r prime over its magnitude. That gets us the unit tangent vector. And so then the dot product of f with t ds would be the dot product of f with r prime of t over the magnitude of r prime of t. And then ds from, I believe it would be, what is that page? Where is our ds? Right here. Page 135. And you'll notice that they both have a magnitude of r prime, and so in fact you just get f and the dot product with r prime dt. And so what we'd want to do then is we would want to integrate those. That r prime of t dt is what we will notate, we'll call that dr just for notation's sake. And so what you end up with then, to find the work, to find evaluate a line integral on a vector field, we're going to use it for work in this example, but this is true for any line integral. You have this f dot product with dr, which is the same as f the dot product with the unit tangent vector ds, which is equivalent to integrating from a to b where these are t values of f of x of t, y of t, z of t, r prime of t dt. So it's typically the last form that we will use to actually do the integral. So let's try a couple of examples. We're going to do one in 3 dimensions here first. Find the total work done on an object traveling along the path given by r of t, so that's the path that it's traveling on, from 0 to 2 pi, so those are t values, given by the force, or by the force field given by this. So this is find the work done on an object, find the total work done on an object by this force field. How much work is done on the object? So the object is moving through a force field. How much work is done by the force field moving it that direction? Okay, so we are going to do the line integral of f and the dot product with dr. Well, that's the line integral. F is equal to negative, let's see, x is cosine of t, And then negative y, y is sine of t, so negative sine of t. And then z is t, so negative t. And then the dot product with r prime is negative sine of t cosine of t1 dt. Now let's simplify that. Let's see. We have cosine of t sine of t minus, oh, that's convenient, sine of t cosine of t minus t dt. And t here is going from 0 to 2 pi. What we have here is we have a helix. Right, so we have the unit circle, cosine of t, sine of t, but then z varies t. So we're traveling up a helix. We're just going, I'm kind of going too far. We're just going one rotation. T is going from 0 to 2 pi. We're just going one rotation. This is convenient here. We just get the integral from 0 to 2 pi of negative t dt, which is, we go scroll down here, negative 1/2 t squared from 0 to 2 pi. That's negative 1/2 times 2 pi squared, so that would be negative 2 pi squared. Now you might wonder, why is that negative? This is work done. That's a little weird. So let me jump over to the maple graphic of this here. So here you can see the blue line is the helix. That's the helix that we're traveling on. And then these arrows are the force, negative x, negative y, negative z. We can't really see, but the components are all negative. So as x, y, and z increase, as you get further from the center, they get larger and they're pointing you toward the center. If we zoom in, you can see here that they're all pointing down. They're all pointing down into the toward the origin. So the issue is, this is not actually the work done by the field. We're actually moving against the field as we spiral up. So this is actually, because the answer is negative, this is actually the work done that it would take to move the object up that helix, up one rotation, working against this force field. So if you get a negative answer, that's actually the work it takes to move the object through the force field. Okay, we can actually do line integrals, just a straight up line integral without any context as well. So let's do this here. Think of this now as just a skill you're learning how to do a line integral, and we'll talk about more meaning as we progress throughout the course. First of all, this is another one of these where we have this curve and it's kind of implied what the curve is, but it isn't really clear. So this one, I don't know if you can tell from the points, there's 1, 1, and 2, 8. We're going to assume that is y equals x cubed. That's the path. So one possible way to write the path would be to say, well, let's let x be t, and then y would be t cubed. Okay, so our force field is x and 2y. So along that path, the force field will be equal to t and then 2t cubed. All right, so the line integral, I don't know, can you hear the kids in the background? Hopefully the mic doesn't pick them up. They're like playing Fortnite in the background. It's like in another room, the door is closed, but what can you do? All right, so this will be the integral. Let's see, we have f, so t and 2t cubed, dot product with r prime, which would be 1, 3t squared dt. And let's t, if we want to travel the full path, t here would be 0, t equals 0, and since x is equal to t, it'll end up at t equal 2, so 0 to 2. Let's see, what do we get there? We get t plus 6t to the 5th dt. And I'll let you evaluate that integral. It's pretty straightforward. You get 66. That's just a Calc 1 integral. Line integrals are not Calc 1, but the integrals you end up with, they're just integrals in terms of t. So they just usually end up with Calc 1 integrals. But a line integral itself, that concept of a line integral, vectors, dot products, definitely not Calc 1. Okay, one other thing here that we're going to do, and then we're going to do one last application here, is a different way to look at line integrals. It's the differential form. And this is going to be useful as we progress through this last chapter. Well, let's consider f of xy, this vector field, to be some function m of xy as the x component, and then another function n of xy to be the y component. And let's assume we have a path r of t, where x is a function of t and y is a function of t, and that t is between a and b. So the line integral over our path c of our vector field, the dot product with dr, would be equal to the integral from a to b, because t goes from a to b, of m, now the vector field mn, and then the dot product with r prime, which would be x prime of t, y prime of t, dt. And if we find that dot product, we will have m times x prime of t. Whoops. There's parentheses there. So we find the dot product, we multiply the m times x prime plus n times y prime dt. And if we write x prime and y prime in terms of their derivative notation, this would be m times dx dt plus n times dy dt. But if we distribute the dt, now interestingly, we get this integral. I'm going to call it the integral over the curve again. We get this integral over the curve, and it is just the integral of m dx plus n dy. Now that form, we're going to kind of put a little asterisk by that. We might reference this later on in the course. This particular form, believe it or not, is sometimes useful. We'll come back to that. But for now, if we keep going and say, well, what if I started with the differential form? Well, that would be the integral of the curve. M would be, where'd my m go? Say for the previous example, say for example 4. The m was x, which was t. Dx would be dt. And then it was the n was 2y, so 2 times, and the y of t was t cubed, and then y prime dy dt dy was 3t squared dt from 0 to 2, and that's the same integral. That's the same integral that we did. Whoops. Sorry. dt. So that's the same integral. That's also 66. So right now this might seem like a little trivia, like why are we doing this? We're just kind of messing around with the variables. We're just planting the seed. This will be useful later on. All right, last page, and these are concepts that will follow us now through the rest of the semester: circulation and flux. So suppose we have a continuous vector field, F, on a region D, and C is a smooth, closed, oriented curve. So it's in a particular direction. So say here's my path C, and say it's oriented. So it has an orientation, it has a direction. And F is some field that is what kind of covers the region where C is defined. The circulation of F is the measure of how much of the vector field points in the direction of C. So if you have a vector field that's maybe, I got some stuff pointed like this, maybe it angles down over here, maybe it curves back over here. How much of that vector field points in the direction of C? Okay, so let's do an example. We have an example here of an ellipse here. This is a tilted ellipse. And then you have the vector field z, x, negative y. we're going to find the circulation. Whoops, we didn't really give the formula. The circulation is just the line integral. It is just the line integral of the field over that closed curve. So that is just the line integral. We could do it this way as well. Okay. So let's try that here. The circulation is just going to be the line integral. Let's find r prime, negative sine of t, cosine of t, negative sine of t. The line integral over the curve, let's see, we're going from 0 to 2 pi. The field will be z, which is negative sine of t, x, which is also negative sine of t. Oh, no, that's for the derivative. Z is cosine of t, x is also cosine of t, and then the opposite of y will be negative sine of t. So that's my field. And then we're doing a dot product with the r prime of t dt. Negative sine of t, cosine of t, negative sine of t dt. Let's take a look here. Hopefully this will end up being a nice one with all these trig ones. We'll see. Let's see. We'll get negative cosine of t sine of t plus cosine squared t plus sine squared t. Ooh, not quite what we had hoped. That's okay. Let's see dt. So we get not too bad of an integral. We get 1 minus cosine of t sine of t dt. So not too bad. We could do a u substitution here. If u is sine of t, du is cosine of t dt. So it's all set up. The integral of, just ignoring the, just doing it as an indefinite integral here. That would just be the integral of u du, and so that's just 1/2 u squared plus c. So that's what we're going to have here. The integral of 1 will be t, and then we'll have 1/2 sine squared t from 0 to 2 pi, which will be, let's see, 2 pi minus 1/2 times sine squared of 2 pi. That'll just be 0, right? Minus 0 minus 1/2 sine squared of 0, also 0, and so we get 2 pi. So the circulation there is 2 pi. What that means is there's, the sum of the forces in the direction of this oriented ellipse are positive. There's a positive circulation along that tilted ellipse. The last one here, we're not going to do an example of it, but similar to the circulation, this one's a little harder to draw in 3 dimensions, so we'll just do it in 2. If we have an ellipse, or some kind of, actually this is just a path C, and again we have an orientation. There's an orientation here. Similar to the circulation, we call the flux of a 2D vector field on a 2D path is a measure of how much of the vector field points in the direction normal to C. So this is only going to be in 2 dimensions where we're going to do this, because if you have a path in 3 dimensions, think of this pen. If I have a particular point here, there are infinitely many vectors that are orthogonal to that, so it doesn't really make sense to talk about it. So this is just in 2 dimensions. The flux is going to be the integral over the curve, and if we want to find normal to it, you can imagine looking at the normal vector. So that's the integral of the dot product with the normal vector rather than the tangent vector. And that normal vector you can find by taking the cross product of the tangent vector with the k, with the vector, just the k vector 1 in the z direction. Okay, that is it for this video.